deploy with confidence in a very regular fashion. Why was each server different? It was because, let's go on, we were doing this. Our engineers would basically, we would write shell scripts and whatnot in Bash, and we would launch a whole bunch of terminal windows, and then we will SSH and transfer code to production, and then we'll do a service restart. And then some engineers, when they encounter bugs, they'll SSH in and fix it dynamically in production. So you can imagine why Snowflake infrastructure. And we kept growing, right? Even though our service was crashing, it was such, we had so much of value in the market that people still kept using us, even though we kept crashing. So we kept growing, and then because the development environments and the staging environments were completely different from production, and when I say completely different, libraries would have different versions, you'd run different operating systems, all sorts of things. Developers would just throw the problems to the ops team to resolve, right? Like, oh, it's not my problem. I've already wrote the code, now it's your problem to run it in production. so that actually happened. Okay, let's move on. So all of those are bad enough, but actually all of those are actually reasonably simple. Where we really struggled was database challenges. And databases are very interesting. Databases are very interesting because they're not like compute. When you've got poor algorithms, one way that you can solve poor algorithmic behavior, throw more CPUs at it, you scale horizontally. It's possible. It's not ideal, but it's possible. Databases, you can't do that. There's no such thing as throwing more databases at it, right? If all your data resides in one database, you can't like spin up another database and automatically the problem is solved. You'll need to think about sharding, you'll need to talk about balancing, you've got to figure out what's the key that you're going to shard on. You're going to worry about all that stuff. So the problems that we had was that our workload was exceedingly poor. It was so bad, I can't quite describe how bad it was. But as bad as the workload is, I will say this. You're using MySQL. Many people blame MySQL when actually it's not MySQL at fault. It's actually the workload that is at fault. And MySQL can take a lot of punishment. And InnoDB, the engine, I think, which is an excellent relational engine for MySQL. The InnoDB engine can take a lot of punishment, and we were running on the biggest instance on RDS, and our workload was so bad, we actually exploited a whole bunch of bugs within MySQL itself. I remember once that it crashed the database, and it took the AWS engineers 12 hours to restore it. And in that time, because they had troubles restoring it, they found bugs in MySQL, they found bugs in the underlying network driver that was powering that RDS instance. And we had 7 global AWS VPs on the phone with us to explain how can this happen. That's how, basically our workload was really bad. Now, just to give you an example of the scale that we were operating at, I want to give you 3 interesting numbers. We had one of our smallest tables, and maybe it was the smallest table, was our drivers table. At that point, we had maybe 60,000 drivers. So that was one of our smallest tables. And then we had another table, we called it our candidates table. We had about 1 billion rows in it, and we were doing about 6 million inserts an hour at peak. And then Postgres, we were doing about 100 million let longs insertions a month, which is 500,000 an hour at peak. Now, we looked at this and we thought to ourselves, where could the problem be with our database? And it turned out, so we spent a lot of time on this and this. We spent maybe about a year trying to optimize this too. And these two were not ideal in any way. That second table, the candidates table, we were doing, there was high number of inserts, which in itself are not bad. Then we were doing high number of updates, which are really bad, because whenever you do an update, you've got to lock the index, and then you've got to go and write the data, and then you've got to unlock the index, and that in itself, locking, there's nothing that hurts locking, nothing that hurts performance more than locking, so that's really bad. But there was no deletes, right? So we thought that was bad, so we optimized for it, which helped, but it didn't help that much. And I'll talk about that in a second. But if you can move on, that was not the biggest source of our problem. The biggest source of our problems was actually the drivers table. The smallest table was the biggest source of our problem. And we didn't understand it yet because our database kung fu was not very good. But at that point, our database, when I said that we had bad workload, we were doing queries where we were joining 5 different tables. And joining 5 different tables is not great, but in almost all our queries, what we would join against is that drivers table. And the moment when everything joins against the drivers table, and at the same time you are doing inserts and you're doing updates on the drivers table to change the driver state, what happens is that every single time MySQL has got to go and build locks, and then the moment things are locked, nothing else can proceed. Now, what would happen is that sometimes we would have cases where there is incredible amount of load coming in, legitimate passenger load. I'll give one example. When the MRT failed in Singapore, all the passengers decided to use Grab that day. So all of them started making bookings. Guess what? This table, everything got blocked. Now, when there's high deal of concurrency, what MySQL does is that it builds mutexes around parts of the code base which are not very, which basically need to be protected against concurrent access. And you get this, right? This is a graph of mutex read and writes, and you can see at certain points it just spikes. The moment it spikes, if MySQL cannot resolve that lock or that in time, and there's more load coming in, then you have more locks that build up, and that just leads to a cascading failure. So really, our biggest problem was our smallest table. Let's move on. And the way you know one very defining characteristic of a very bad or poor workload, which is exemplified by mutex logs, is this sort of behavior on your database. You'd be doing fine at maybe 15% CPU, and then bam, you have a straight spike up there. What's happening here is that your database is basically has built up locks, and then all it's doing is that it's jumping. These are what are known as spin locks in computer science terminology. Everything that MySQL InnoDB engine is doing is that it's just polling the locks and it's checking: are you free? Can you be is this lock available to be used? Is this available to be used? So that polling is what leads to the spike in the CPU. The moment you hit more than 80% CPU, basically your database is not doing anything useful. All it's doing is just jumping from lock to lock to lock. At that point, it's all downhill. There's nothing much you can do. You can kill the queries, and as we did, hopefully it'll recover. But if you've got lots of legitimate demand coming in, this is just a spiraling bad situation. You really just need to fix the underlying problem, which is just very, very poor workload. So, I will go into how we solved it.
Anyone any questions in the meantime before we jump ahead? Because we've got another talk, and Ditesh is just going to go into what we're doing today, but